Welcome to another practical physics walkthrough, and today we are going to have a look at the force due to a current, so sometimes called force on a current carrying conductor. And effectively what we're going to do is use a balance, simple tabletop balance, set of magnets and a bit of wire, wang a current through the wire and look at the force that gets applied to it, to the magnets, by just looking at what the apparent increase in mass or weight on the balance is. So there's three variations of this, and you're definitely going to do two of them. So the two that you'll probably do is changing the current and the length, but if you've got time you can also do changing the number of magnets. So let's have a look at the kit. We've got balance, an ammeter which we've got set on the DC scale, and probably safer if you put it on the 10 amp for now, and we've got a continuously variable power supply, and then up on the shelves there's a little set of kits marked current balance, and inside here you get a little groovy 3D printed yoke, bit of wire that's been bent just so, and a set of 5 magnets. Once you've got that, you're away. So setting it up, you'll also need a retort stand and this little wire assembly has just been pegged into the retort stand somehow, and we're just going to pop that over the back so that it works with the little 3D printed yoke. And what you can see is that we're just going to slot that into there, make sure the yoke's in the middle, make sure the wire's inside that slot, make sure it's all nice and level. That looks pretty good. So you can now see that I would normally have it that I don't have my wires trailing all over the place like this, but to see it in the frame was a bit awkward. So let's just make sure that is, we don't want it dangling onto the balance, that's the big thing. Yeah, that just about works. Yeah, you can see everything. We don't have to keep subtracting the mass of the magnets and the balance off there, so what we'll do is just tear the balance and we're away. We're going to have to keep doing that as we have the magnets. In fact, we're going to work with all 5 magnets to start with. You'll notice they've got a black and a white arm to denote north and south. You'll also notice these little keepers. These little keepers keep the magnet, so one, they don't attach to something else, and two, they do not, so hopefully you could see that, they do not lose their magnetism. So when you put them into the yoke, all you're going to do is just make sure, because we want a constant field between, these two little bits here. I'm struggling to keep all this in shot, so we need to make sure that all the norths and all the souths are aligned, so you have all the blacks. Do not lose these keepers. Plug those in, take the keeper off, put it somewhere safe, chuck the magnet in, and we're going to look to sort of make sure these magnets are evenly spaced out on the yoke. Whoops. So evenly spaced out on the yoke. Can't get in there, you daft thing. There we go. So that can be a little bit fiddly. I'm just going to space them out slightly. Oh, come on. And sometimes you'll find one pops off, that's just a bit annoying. But as soon as they're spaced out, you should be okay. Why is that doing that? It's not quite making contact. Right, lovely. So after a bit of faffing, we've got our magnets inside that yoke. We've got this wire nicely in the middle of that slot, and we've got our power supply on DC because we want a direct current for this. Make sure it starts at 0. We can tear that balance, and now as we increase the current, okay, so we're actually pulling this up at the moment rather than pushing it down. That's a smidge annoying, but doesn't really make a difference. The force should be the same pull or push. I am going to swap it round. So by reversing the direction of the current through here, rather than the force being pulling up on the magnets, the force is now going to be pushing down on the magnets. And you may remember from GC, or if you've seen it in class, the left-hand rule. So force, field, current, the field's doing this, the current's doing this, it's pulling up. We've just reversed the current to go that way, so now the force is pushing down. So let's try that again. So you can see that, and we're not going to take that current above, certainly above 2.5 amps. Okay, but you can see I've got a couple of grams there, so I should be able to get 10 different readings quite easily, certainly 8. And that will be enough for me to compare my current with the force down. For the second bit of the experiment, it's as simple as this. Let's just set it at a couple of amps. Sometimes easier said than done. It doesn't have to be exactly a couple of amps. I'll just have it there roughly. Now what I can do is, if I measure the amount of wire that's within here, as I move it out, it's only the length of the conductor that's actually within the magnetic field that causes the force. So as that length decreases, you can see that the force decreases. Okay. And so bring it out. So okay, we're going to take the length, we're going to take the fields only existing within that orange yoke. You can see that's not strictly true, but hopefully you can see that effect. And each time you make a movement, you'll have to just measure the length of the wire within here. If you're clever, you can probably make some markings on the wire itself. Just remember to clean them off at the end. For the final experiment, you would just have to remove one magnet at a time. Obviously only 5 magnets in there, so you can only take 5 readings. Just be careful to turn the balance off at the end, and then I can turn it off at the plug. So that was the different variations of that experiment. Hopefully you'll find that useful when you come to do it, and that you enjoy investigating the force due to a current carrying conductor.